Welcome to the natural log function integration. In the previous video, we took the derivative of the natural log function and saw that the derivative of the natural log of x was 1 over x. And then we also saw that if we took the natural log of u, it was u prime over u. These are the different ways that we can write the rule for integration, which again is kind of going backwards from differentiation. So if u is a differentiable function of x, we have the general rule that the integral of 1 over x dx is the natural log of the absolute value of x, and then of course plus c for any indefinite integral. And number 2, it's just simply using u. Now, if something is a little more complex than 1 over x, if let's say we have u prime over u, or some expression and then its derivative in the numerator, when we take the integral of u prime over u dx, we get the natural log of the absolute value of u plus c. This is called the quotient form or the alternate form of the log rule. So in your notes, I do recommend that you have one of these two written down. They're essentially the same idea. And then also this quotient form of the log rule for integration. We previously studied the power rule for integration, and we saw that if we were taking the integral of x to the n dx, it would give us x to the n plus 1 and then divided by n plus 1, or 1 over n plus 1 out in front, and of course plus c. Now this rule did not work when n was negative 1, and that is because x to the negative 1 is the same as 1 over x. That is the log rule for integration. So the log rule is what happens when n is negative 1. So if we have x to the negative 1 dx, so that is the integral of 1 over x dx we just saw, that ends up being the natural log of x, the absolute value of x, plus c. So the power rule for integration we can use anytime that we're integrating x to the n, so long as that n is not negative 1, and we don't have x to the negative 1 or 1 over x. If we do have x to the negative 1, aka 1 over x, we have to use the log rule for integration instead. So they are very similar rules in a sense of how they look from the start, but in this section we will be exploring when that exponent is negative 1. Let's take a look at 3 simple examples using the log rule for integration. You can see that I've snipped the log rule up here. In this first one, it's literally the form, the integral of 1 over x dx. We can see what that's going to be pretty easily. This is going to equal the natural log of the absolute value of x plus c. In our second example here with the pink star, we see that we have something very similar, but I'm just going to rewrite this before integrating. We can bring that 2 out front, and then we can see that it's 2 times the integral of 1 over x dx. Well, that's clearly going to be 2 times this natural log of the absolute value of x. So 2 times ln of the absolute value of x plus c. Then, using the properties of logs that we explored more in depth in the previous video, we can actually bring that 2 to the exponent of the x. Now, if you think about this, we're going to end up having x squared, the natural log of x squared, and then still plus c. We no longer need to have these absolute value bars here around the x squared because no matter what x is, x squared is always positive. So instead, we can just change those to parentheses. In our third example with the orange star, we're going to do this in a very similar way and bring this 3 out front just to show that it will end up being 3 times the natural log of the absolute value of x plus c. Using that same idea, we'll have the natural log of x cubed plus c. However, x cubed and x squared are different in that x here could end up being a negative number, and if it is, if we cube it, we still have a negative. Therefore, the absolute value bars are still necessary here, whereas over here with x squared, they're not. Let's take a look at some other simple looking integrals here. So the integrand here, 1 over 4x minus 1, is fairly simple. We are actually seeing that this is a form of 1 over x dx. It's just a little bit fancier in the denominator. It's 4 times x, and then there's a minus 1. Same with over here, pretty similar idea. Well, we can clearly see that this is going to be a natural log rule for integration, and we can see that by doing a U-Substitution. So let's let u equal our denominator here. So if we let u equal 4x minus 1, we can see that du is actually going to be 4 dx, and therefore 1/4 du is just dx, which we have right here. So replacing this integral solely in terms of u will give us the integral of 1 over u, right here, and then dx will get replaced with 1/4 du. So I'm going to actually write the 1/4 out in front and the du inside. This looks like the original form for the natural log form to integrate. So we can see that the integral of 1 over u du is simply the natural log of the absolute value of u plus c. This is exactly the same as 1 over x dx, and this is x right here, just showing in a couple different forms. So we're clearly going to get 1/4 still out front times the natural log of the absolute value of u plus c. Now our original problem was, of course, in terms of x, and this answer here is in terms of u, so we need to back substitute and go back to our original variable. I'm going to replace u with what we set it equal to, 4x minus 1. So our final answer is 1/4 the natural log of the absolute value of 4x minus 1 plus c. In our next example over here, we have the integral of 2 over 5 minus x dx. The first thing that I would recommend doing is simply just bringing that 2 out in front so it's a little less complicated. Of course, you do not have to do this. It's just something I like to do. Then we can see that we have 1 over something, and that something is just an expression with x to the first power. Essentially, that means we're going to need to do a U-substitution and get a natural log out in the end. So let's let u be our denominator. So u will equal 5 minus x. And then following that, its derivative du is -1, the coefficient of x there, dx. Now, I don't want -1 dx because that's not a part of the integrand, but 1 dx is, or just dx. So we'll divide both sides by -1 and get that dx can be replaced with -1 du. All right, now we want to rewrite our integral. So we'll have the 2 out in front. Inside, 1 over 5 minus x becomes 1 over u. Then dx can be replaced with what it equals, which is -1 du. We'll bring that -1 out in front, which makes the 2 negative, and we'll have du on the inside. Then using our rule, we'll have -2, the natural log of u plus c. So we finally integrated there using our rule. Then we want to back substitute, of course, because our original problem is in terms of x, not u. We'll replace u with what it equals, which is 5 minus x, close the absolute value, plus c. All right, we've done both of these and did a U-substitution. We're actually going to see further along in the video that we don't necessarily have to go through this whole process of a U-substitution, and we can instead do something a little bit quicker if it's a problem that kind of fits a certain form, so we'll see that in just a minute. But what I want to do now is check one of these answers with differentiation. Remember that differentiation and integration are kind of, I hate to say opposites, but they go back and forth with each other. So we can check our answers using differentiation. I'm going to pick this one to do. So let's check our answer here and see that we get back with what we started. So I'm going to take the derivative with respect to x of our answer here. So we are taking the derivative of what we got for the first example. If we look back from our previous video, we see that if we're taking the derivative of the natural log of the absolute value of u, we end up getting u prime over u. So in this case, our u is 4x minus 1, and then our u prime would end up being 4. So when taking this derivative here, we'll still have the 1/4 out in front. This right here, the natural log of the absolute value of 4x minus 1, using our derivative rule, we'll get 4 over 4x minus 1. And then plus c, the derivative of that is 0. When we take these two multiplied by each other, the 4's end up canceling top to bottom. So we're ending up with 1 over 4x minus 1, which was our initial integrand of our problem. So we did find the integral correctly here, and we checked our answer using differentiation. This next example is showing, again, that finding the definite integral of a function is essentially finding the area of a region under that function down to the x-axis. So in this case, we want to find the area of the region bounded by the graph of y equals x over x squared plus 1, right here, the x-axis, and the line x equals 3. So based on this graph, we can see that we are being bounded by the x-axis, so we're only going down to the x-axis, and since this function hits at the origin 0, 0, we're starting also at x equals 0 at the y-axis. Then we're also bounded by x equals 3. So the area of this region is represented by the definite integral from 0 to 3, those are our x values, of the function x over x squared plus 1, variable of integration x dx. All right, we can see that in this quotient in here, we have a denominator, x squared plus 1, and the derivative of that denominator would be 2x, which we have sort of the meat of that derivative up top. No, it's not 2x, but it's very close. Earlier in the video, we talked about the alternate or quotient form of the natural log rule for integration right here. And that tells us, it's sort of like a shortcut way, so we don't have to do an entire U-substitution, which you of course could do still, but let's explore this kind of shortcut way to make life simpler for evaluating this definite integral. It tells us that when we have the integral of u prime over u, still in terms of x, it gives us the natural log of the absolute value of u plus c. No need for a long U-substitution. Well, do we have that here? Okay, our u here would be x squared plus 1. What would u prime have to be? It would have to be 2x. We're so close. But instead, let's just set it up that way, and let's say we did have this. This is the quotient form that we want. It's very close to this, but it's not the same function. What can we add out front, or what can we multiply by out front to make blue equal to pink? Well, since we have a 2x in here, we had to multiply by 2. Let's undo that by dividing by 2 out in front. Now these are equivalent integrals. So we did this in here so we could get this quotient form. The reason we did that, again, is because it's a quick sort of output to figure out what the integral equals. So we can see that our u value is x squared plus 1, its derivative u prime is up top, and we're still in terms of x dx here. These are just kind of a shortcut way to view it when you have an expression and then its derivative above it. That is going to give us the natural log of the denominator, plus c. Now, in this case, we're not going to have a plus c because it's a definite integral. So let's integrate this. This will be 1/2 the natural log of the absolute value of x squared plus 1. And then, like we said, we're not going to have plus c, but instead we're going to evaluate this from 0 to 3. Recall the first fundamental theorem of calculus tells us we need to first plug in 3, so we'll have 1/2 the natural log, and then I don't need the absolute value anymore because this will be a positive number. This will be 10 when we plug in 3. And then minus evaluating at our lower limit of integration, which is 0. So if we plug 0 in here, we'll have 1/2 the natural log of 0 squared, 0, plus 1, which gives us the natural log of 1. Now this first term here, we'll need a calculator. It gives us approximately 1.151. And then our second term, the natural log of 1 is just 0, so 1/2 times 0 is 0, so I should put an approximate symbol here. It's approximately 1.151. So the area underneath this curve, down to the x-axis from x is 0 to x is 3, is approximately 1.151 square units. We just saw our first example using the quotient form of the log rule. Let's take a look at a few more examples of this form. So the quotient form, once again, is when we have the integral of u prime over u, but still in terms of x, so not using a full-on U-substitution. That outputs, in a simple way, the natural log of the absolute value of the denominator, plus c. Here we will have plus c's because we do not have limits of integration. These are indefinite integrals. In part A, we can see that our u value, our denominator, is x cubed plus x. Then u prime is sitting pretty right up top. It would be 3x squared plus 1. So we have a u prime over a u. It's perfectly set up. We don't need to multiply by anything out front. We have exactly what we want. So our u here is x cubed plus x. So this outputs to be the natural log of the absolute value of x cubed plus x plus c. It's as easy as 1, 2, x to the 3. In part B, we can see that we have the exact setup here as well. Now for these, I do recommend that you have your derivative rule sheet or your derivatives reference sheet handy, because we might have forgotten that the derivative of tangent is secant squared. So we again have u in the denominator, and then u prime, its derivative, sitting up top. This is going to output to the natural log of the denominator, the absolute value of the denominator, plus c. Now again, why does this work? We already explored this once, but in the previous video we talked about the derivative of a natural log function involving absolute value. When we're taking the derivative of the natural log of the absolute value of u, we end up getting 1 over u times its derivative u prime, or u prime over u. This is essentially just going backwards and taking the integral of that u prime over u, and that gives us the natural log of the absolute value of u. Here in parts C and D, we are again seeing that we have basically the quotient form of the log rule. Now in part C, you can see that we don't exactly have the quotient form perfectly like we did in parts A and B. And that's because our denominator here, u, is x squared plus 2x. Its derivative u prime would be 2x plus 2, which we don't exactly have. But calculus students are resilient and we can get this figured out. So let's say we know that u is x squared plus 2x, and then u prime is 2x plus 2, or 2 times what we already have up there, 2 times x plus 1. So let's rewrite this. Let's rewrite this as the integral of u prime over u. So this will end up being u prime, which is 2 times x plus 1, over u, which is x squared plus 2x dx. Now these aren't exactly equal yet. I shouldn't put this equal sign here yet because we're not quite equal. But how can we get equal? How can we make blue equal to black? Well, we multiplied by 2 to get from here to here. So out front, in order to keep it equal and balanced out, we have to divide by 2 or multiply by 1/2. And there we go. We have equivalent integrals now with this 1/2 out in front. Again, the reason we're doing this is so it looks like the integral of u prime over u, and this is a nice little shortcut to integrating. So we'll have, using our rule and integrating, 1/2 times the natural log of the absolute value of our u, which is our denominator, x squared plus 2x, close, and then plus c. In our next example, I have a little note here that says look back, because we actually did this one earlier in the video and we did a full-on U-substitution for it. We can actually take advantage of this easier way of doing this and using this quotient form of the log rule here instead. So we already know what we should get as our answer here because we did it earlier, but we want it to look like the quotient form this time and show a different way. So our u here would be our denominator, 4x minus 1, and then u prime, its derivative, would be 4, which we don't have. But instead, I want to make it look like that. So I want my integral to be my u in the denominator, and then u prime up in the numerator. Now these are not equal yet. I multiplied this original one that we want to integrate by 4. So in order to balance it out, I have to multiply by its reciprocal out front, 1/4. Now these two are equal, and we can use our shortcut here, the quotient form, in order to integrate. So this is going to equal the 1/4 out in front, the natural log of u, which is 4x minus 1, and it's the absolute value of that, and then plus c, which is what we got earlier when doing a full-on U-substitution. This is just, like I said, again, a shortcut of a U-substitution if you have something of the form or close to this quotient. This next example I called a challenging example because it is a little bit more challenging than the ones we've seen so far, but it's not too bad. Let's see if this looks like the quotient form at all. Our denominator is x plus 1 quantity squared. So let's just say we wanted to. Let's just see if it looks like that quotient form of the integral of u prime over u dx. In this case, our u would have to be x plus 1 quantity squared, And then u prime, using the chain rule, would be the 2 out front. This end up raised to the first and then multiply by the derivative of the inside, which is just 1. Okay, so we don't have that. This would be 2x plus 2. We have the 2x part. This is not going to end up fitting because we can't easily just add and subtract a number here when we have this quotient, this fraction. In the previous examples, if we didn't have exactly the u prime we needed, it was just a multiplication issue. When it's addition or subtraction, it's a bit more difficult and is not going to work. So this is looking like we're probably going to need a full-on U-substitution here and to actually change the variables. So let's let u just equal what's in parentheses and see if that can work. Then du would simply just be 1 dx. Now that's an issue because the denominator I can replace now with u. It's just u squared. But we have this 2x up here. What we're going to do is we're actually going to solve this up top for x. So solving u equals x plus 1 for x will give us that x equals u minus 1 when we subtract 1 from both sides. And this is important because now we can replace x with something in terms of u. So replacing this integral and writing it solely in terms of u will look like this. Our numerator will be 2 times x. X is u minus 1. So it's 2 times u minus 1. The denominator, x plus 1 to the second, will be u to the second. And then our dx is replaced with du. Now what we have is we have a common denominator to our numerator here, which is 2u minus 2, and it's all over u squared. Yes, you could bring that 2 out front if you wanted to do that as well. I'm just going to skip doing that in this case. Then we'll have the integral. We can break this apart into two separate fractions. We'll have the integral of 2u over u squared, and then plus, or minus rather, minus 2 over u squared, and then of course du. Now we can cancel, this is just going to be 2 over u in this first fraction here. So we'll have the integral of 2 over u minus 2 over u squared du. We can write this as two separate integrals if we want, and if you'd like to do that, I'm doing a lot of different work here. We can bring the 2 out front, so this is 2 times 1 over u du, and then this is minus 2, the integral of u to the negative 2 du. So I simply brought the 2 out front in these two cases, split them up into two separate integrals. Again, totally your preference. Now, in the first integral, we can see that this is just going to be a natural log of u, of the absolute value of u. So this will be 2 times the natural log of the absolute value of u, and then we'll wait to do the plus c until we've integrated everything. Over here, we can see we have u to the n, just like we did here, but in this case, n is not negative 1, so we're going to use the power rule for integration here. So we'll have a minus 2 out front still, and then we're going to raise u to 1 more. So negative 2 plus 1 is negative 1, and that's the number we're also dividing by. And then we'll have our plus c. Cleaning up here, this is just going to end up being a plus 2, and then over u, since it's u to the negative 1, plus c. Now we have successfully integrated using u, but our last step is to go back to x, to back substitute. So all of our u's will be replaced with x plus 1. So we'll have 2 times the natural log of the absolute value of x plus 1 plus 2 over x plus 1 plus c. The last main part of our video will be the integrals of our 6 basic trig functions. Now our 6 basic trig functions are right here. We already know the integral of sine is negative cosine, and the integral of cosine is sine, and that's just working backwards from their derivatives. However, the other 4 trig functions actually have integrals that all involve the natural log. Be sure that you have these 6 rules written down. They are also on your integrals reference sheet, but just be sure that you have them because some of them are a little bit intricate. Here I'm going to do the proof of why the integral of tangent of u du equals what it equals. Now I'm just going to use the variable x instead of u just to avoid some confusion, But here I'm going to prove why it equals negative the natural log of the absolute value of the cosine x plus c. It's kind of a random output, like how do we get this from here? Well, if we take a look at the integral of the tangent of x dx, we can actually replace the tangent of x with what it equals, the building blocks of trig. Tangent is really sine over cosine. Now this looks like the quotient form, meaning in our denominator our u is cosine and our numerator is its derivative. Well, almost. The derivative of cosine is actually negative sine. So we can rewrite it as negative the integral of negative sine of x over the cosine of x dx. So now we have u prime over u, where u is cosine x and u prime is negative sine of x. I put the negative also out front, so these two cancel out and these two end up equaling each other. But we had to get it in the quotient form. So using our rule here, this gives us negative, because we had that negative out in front, the natural log of the absolute value of our u, our denominator, the cosine of x, and then plus c. And we have proved why the integral of the tangent is negative the natural log of cosine plus c. The next one, cotangent, is an extremely similar proof. As you can see, cotangent, just cosine over sine instead, the reciprocal. These other two, the integral of secant and the integral of cosecant, are slightly more complex proofs. The proof of this one right here, the integral of secant being this long output here, natural log, is actually in your book if you're interested in seeing it. Let's delve into some trig examples. I actually have two, and that will close out the video. Our first one, we want to evaluate the definite integral from 0 to pi over 4 of the square root of 1 plus tangent squared of x dx. Now here, however your pre-calculus days went, if you can remember back that far, this is actually a Pythagorean identity. I put them here. The most famous Pythagorean identity, of course, is sine squared plus cosine squared equals 1, but the other ones are that 1 plus tangent squared is secant squared and 1 plus cotangent squared is cosecant squared. They actually all originate from this original one. So 1 plus tangent squared can actually be replaced with secant squared, which we're going to do here. So we will simply replace this integral from 0 to pi over 4 of the square root of secant squared x dx. Again, using the Pythagorean identity to replace this with secant squared. Well, if we take the square root of something squared, we're left simply just with that something. So this is the integral from 0 to pi over 4 of the secant of x dx. We just learned the integral rules for our 6 trig functions. 2 of them we already knew, but the other 4, including secant, involve the natural log. So here is our rule for the integral of secant. We're of course not going to have a plus c because this is a definite integral with limits of integration. However, we just have the secant of x dx here. So it will be the natural log of the absolute value of the secant of x plus the tangent of x. And instead of our plus c, we're going to evaluate this from 0 to pi over 4. The first thing we want to do is plug in pi over 4. Then we'll subtract, plugging in at 0. Now we do have to recall that the secant is the reciprocal of the cosine. The cosine is our x value at these points on the unit circle. Then the tangent is y over x. Let's take a look at pi over 4 first. We can see that at pi over 4, the cosine is root 2 over 2. That means its reciprocal would be 2 over root 2, and when we rationalize by multiplying both top and bottom by root 2, we'll get 2 root 2 over 2, which is just root 2. So the secant at pi over 4 is simply root 2. Then the tangent is y over x. Well, in this case, our y and our x are the same, so the tangent at pi over 4 is just 1. So we can replace the secant of pi over 4 with root 2 and the tangent of pi over 4 with 1. Then we want to do the same thing for the secant at 0 and the tangent at 0. 0 is over here, 0 radians. So the cosine here is 1, which means it's reciprocal. Secant is also 1. Then the tangent here is y over x. 0 over 1 is just 0. So the tangent here at 0 is 0. Let's replace that with what we just found out. The secant of 0 was 1, and the tangent of 0 was 0, so we had plus 0. All right, this looks like we're going to need a calculator. We no longer need the absolute value, technically, because this is a positive number. So the natural log of root 2 plus 1 is 0, or it's approximately rather, so approximately 0.881. And then minus the natural log of 1. The natural log of 1 is just 0. So this is approximately 0.88. Our last example, we want to find the average value of f of x equals the tangent of x on the interval from 0 to pi over 4. So the same interval we had earlier. Now recall, to find average value between a and b is 1 over b minus a multiplied by the integral from a to b of f of x dx. So we're going to have 1 over pi over 4 minus 0, so 1 over pi over 4 times the integral from 0 to pi over 4 of the tangent of x dx. We just learned that the integral rule for the tangent of x dx is negative the natural log of the absolute value of the cosine of x. The first thing I'm going to do here is simply write this as 4 over pi to make it less crazy. And then next, we can rewrite this. This is going to be negative the natural log of the absolute value of the cosine of x. And then instead of a plus c, we're going to evaluate this from 0 to pi over 4. Now this 4 over pi, I'm just going to sort of wait until the very end to multiply by that again. Instead, I'll just do this part here, the definite integral. So the first thing we're going to do is plug in pi over 4. So we'll have negative natural log of the absolute value of the cosine of pi over 4. Then minus negative the natural log of the absolute value of the cosine of 0. Then I guess I'll keep the 4 over pi out front. Why not? We don't want to forget about it. All right, the cosine of pi over 4 using our unit circle is root 2 over 2. So this is negative the natural log of root 2 over 2. Then we'll have minus a negative, so plus the natural log of the cosine of 0. The cosine of 0 is just 1. Well, we know that the natural log of 1 is just 0, so we end up with 4 over pi times negative the natural log of root 2 over 2. Using our calculator, we will get approximately 0.441. In this video, we explored how to integrate the natural log function after learning all about its derivative. We can clearly see the relationship with the natural log function's derivative and integral. We also learned a lot about the quotient form, a simpler way and an alternate way of using our natural log rule for integration. Remember that when we are integrating x to the n, we only use that power rule for integration so long as n is not negative 1. If n is negative 1 and we have x to the negative first, or 1 over x, we are going to be using the log rule and getting out a natural log instead.